In today's video, we want to look at the liquid drop models of the nucleus, and one of the things that we'll be looking at in this nuclear video is to establish the similarities between the nucleus of an atom and that of the liquid drop. That will help us to find the volume energy, the surface energy, and the Coulombic energy. So let's start by looking at what are the similarities that we can think of when we talk about the liquid drop and the nucleus of an atom. The first thing that we would like to talk about would be a kind of comparison to compare between the nucleus of an atom and the drop of a liquid. And that brings us to the first point of this video, as I mentioned, that we are going to talk about the similarities all that exist between this nucleus of an atom and the liquid drop. The liquid drop model, as we always call it. And you can see we have cohesive and adhesive forces. The force of cohesion is nothing but the force of attraction between the molecules of the same substances. Like we have seen here, later in this video, I will be talking about the force of attraction in the nucleus. Then I will explain what you can see here. This PP, this is like proton attracting each other, but we'll be talking about it in the later in this video. We want to show the similarities that exist between this liquid drop and that of the nucleus of an atom. So the first thing that we would talk about in these two things is that they contain large number of particles. When you look at the nucleus of an atom and when you look at the drop model, both the nucleus and the drop of the liquid contains a large number of particles. When we say they contain a large number of particles, what we are talking about, for instance, in the nucleus, what exists in this nucleus, as you can see, is the protons and the neutrons. So the protons and the neutrons are what we are referring to in terms of the nucleus. And the drop model also, as you can see, it contains water molecules. So we are talking about this force tension. That's why you can see the surface tension force. The surface tension force that try to repair the force of attraction that in this liquid drop model. But now these two things make them similar, and you can actually consider the nucleus of an atom to be that of a liquid drop. The second point that we can talk about is what we call homogeneous and incompressible. Both of these nucleus and the drop of the liquid are homogeneous and incompressible. What we mean here is that in the nucleus, for instance, the protons, we know the protons is represented by letter Z. So we can see the protons in the nucleus. We are talking about the nucleus. The protons and the neutrons are what you can see in this nucleus of an atom, and they are uniformly distributed. They are uniformly distributed, and this is the same case you can find also in the drop of a liquid, and this makes them similar and can help us to consider the nucleus of an atom to be that of the liquid drop. The third point is that the nuclear mass density is constant throughout its entire volume, and that is the same case in the drop of a liquid. So we can say here that the nuclear mass density is constant through its entire volume and drop to zero near its boundary surface, just like a liquid drop. I will illustrate this using a kind of graphical representation. Let me explain the third point that we talk about, the mass density, which is constant in terms of the liquid drop model and that of the nucleus. So let's say that we have our x-axis, and our y-axis in this case. have this axis. This is our x-axis, our y-axis, sorry, and this is our x-axis, as we call it. This x-axis represent the rate. We can say this is nothing but the rate of distance, the rate of distances. And in our y-axis we have the mass density, and like I mentioned that the nuclear mass density is constant. So as the rate of distances moves, let's say it moves from this position, it moves from this position in the y-axis straight, it comes up to this point, it must come back to zero, to reduce to zero. We are saying that the nuclear mass density is constant throughout its entire volume and drop to zero. So as you move away from the center of the nucleus, then what happens is that the volume will drop to zero, and that gives us the mass density, which is constant throughout the entire volume and throughout the entire liquid drop. So we are referring to these two things, as you can see them, that they actually mean the same thing when we talk about the nucleus and the liquid drop, and that will help us now to calculate the volume energy, the Coulombic energy, and that of the surface energy. But first of all, let us look at the force of attraction that exists in the nucleus. So note again, as we consider the force of attraction, note again that in your representation here, in this our graphical representation, y-axis, as I mentioned, help us to understand the rate, help us to understand the distances between the force of attraction and the charge density also. But the charge density, as you can see, they are always constant and drop at the surface. It drops at the surface, and this will always be equal to zero, or what we call the state of equilibrium. And this is the relationship that exists between the drop of a liquid and that of the nucleus. So now when we look at the force of attraction, let's say that we have neutron, two neutrons. In this case, we have neutron. We have another neutron. We have neutron, proton. We have neutron, proton. We also have proton, proton. In this case, we can have proton, proton. These representations here help us to understand the strong nuclear interaction, and this nuclear interaction does not only exist in the neutron, it also exists in the neutron, proton, and even in the proton. Having said that, let us try to explain more details by deriving an expression for the binding energy of a nucleus, because that's the only way we can understand this better. So let's come up with an expression for the binding energy of a nucleus. When we try to come up with this expression, let's move this a bit. We want to come up with an expression for the binding energy of the nucleus. We will start by volume energy. As I mentioned earlier, we start by volume energy. In this volume energy, let's say that we have two nucleus, a kind of two nucleons. Let's say we have this and just a minute. We have two nucleus. well. Okay, this is what we have. In line with the volume energy, I want to give you a simple example of a nucleus that have a simple these two nucleons. It has two nucleons. This is a nucleus. Simple example. It has two nucleons. If there are two nucleons, in the nucleus, it will only happen, one interaction will happen in this type of react. There will be only one interaction in the nucleus. Let's take another example so that you will understand this better. So let's suppose, or let me assume that I take U amount of energy. Let's say that I take U amount of energy. This will imply that E, in this case, which is energy, is nothing but U. Is nothing but U. So what will be the binding energy per nucleon? So the binding energy per nucleon, will be nothing but a half U, since I am providing this with U amount of energy. This is more of a simple illustration. So let's say that we take a different scenario, a more complicated scenario, that we have 4 neutrons at the front of the center neutron, and then we have 4 other neutrons at the back of that center of the neutron, and we have another 4 neutrons that is holding that one from the back again. That will be the total of 12 nucleons. That will be a total of 12 nucleons. Now, if we have this type of scenario that we have 12 nucleons, how many interactions are we going to get, and how can we come up with the total binding energy in this type of scenario? Remember that initially we have our binding energy to be equals to a half U, like I indicated here. So now that we have 12 nucleons, this is going to be a half U multiplied by 12. And we know this is 2. So this will simply give you what? 6U. This will be 6U. So what will be the binding energy in this case? So the binding energy is nothing but A multiplied by the binding energy per nucleon. And this is going to be equals to 6U multiplied by A. 6U multiplied by A. A in this case is nothing but the mass number, but because we are trying to relate the total of amount of particles that are present in this nucleus. So A is nothing but the mass number. So therefore, what will be the binding, the volume energy? We can represent that. Let me pick a different color. We want to see what will be the volume energy. You can represent that with EV. So the volume energy in this case, the volume energy will be that energy that we represent as U, which we can call A, small a1. We can call it A1, and this capital A, which is the mass number. And this will give us, you can call this equation 1, but this equation 1 is what we refer to as the volume energy. Now in the next video, we will continue from here to show us what will be now the surface energy. If A1 multiplied by A is the volume energy, what would be the surface energy? Of course, we know that for us to find surface energy, we will need to refer what is surface area, and we know that surface area is nothing but 4 pi r squared. We'll continue in the next video.